Professor Noga Alon. He has a position at Tel Aviv University since 1995, where he has worked on various topics related to combinatorics, graph theory, computer science, many things related to randomization, expanders, the randomization, streaming algorithms, information theory, computational geometry. And he has published over 500 papers and one very influential book, the probabilistic method, on those topics, where he has advised over a dozen PhD students, received many awards. I will maybe skip some: Polia, Bruno, Landauer, the Gödel, the Dijkstra Award, the very prestigious Israeli prize for the top scientist in Israel. And I'm also happy personally because we belong to the same generation. I did my PhD in Israel, and my advisor, my PhD advisor, was the same generation of Micha Perles, the PhD advisor of Noga, which were the fathers of computer science and mathematics in Israel, and then produced the next generations, which were tremendously influential in the development of modern theoretical computer science and combinatorics. And so we are very happy to have Noga here and continue the collaboration with Israel. A few years ago, we organized the first joint meeting of the Mathematical Mexican Society and Israeli Society in Mexico, and hopefully we will continue fostering the collaboration with Israel. Thank you.
Thank you. Okay. Thank you. Thanks for this very nice introduction. And let me thank the organizers for the invitation, for this perfectly organized meeting. Of course, there is still some room for possible disasters, and this talk may happen to be one of them, but I think it's clear that this is a very nice conference already. And for me, this is the first time in Mexico City. It's indeed a very interesting city, and I want also to congratulate you for this 75th anniversary. Hopefully, for the 100th anniversary, I'll already be able to understand Spanish also. Unfortunately, this is not the case yet, but okay. So I'll be talking about structure, randomness, and universality in graph theory, and I'll explain what I mean by each of these words. And let me start by telling you what's the basic structures that I'll consider in this lecture. So basically, I'll have graphs, and all the graphs I will consider will be finite and undirected. I denote always a graph by a pair VE. V will be the set of vertices, E will be the set of edges. So the graph that you see here has 5 vertices and 6 edges. Okay, now I want also the notion of a subgraph. So a subgraph is what you see here in red. We just take some of the vertices and some of the edges, and we only have to make sure that what we took is itself a graph, meaning that if I take some edge, then I have to take the 2 endpoints of it also for my subgraph. So this is just an example of subgraph. And then I'll have also the notion of an induced subgraph. By an induced subgraph, we mean that we take some set of vertices and we take all the edges that are spanned on these vertices. So all the edges that have both endpoints in the set of vertices that we took. And because of this, the example that we saw before is not induced because this edge, we didn't take it, and this one is induced. Okay, so we'll have graphs we'll have subgraphs, and we'll have induced subgraphs. And now let me tell you what we mean by universal. So a graph G, we say that it is universal for some family, and all my families will be finite, although one can consider the infinite case as well. So it is universal for some family F of graphs if just it contains every member of this family F as a subgraph. Okay, so this is it's a universal structure in the sense that it contains every substructure as a subgraph. And a basic question that we want to consider, and I'll tell you that this has been considered quite extensively, is to try to find small universal graphs for given interesting families. So what we want is to determine or estimate the minimum possible number of edges in a universal graph for some interesting family of graphs with at most k vertices. We will get some interesting family, like maybe the set of all planar graphs on k vertices, or all the trees or forests on k vertices, and we'll want to have something which is pretty sparse, does not contain too many edges, and contain all of them as subgraphs. Okay, so just to tell you something about interesting families that have been considered, and I'll not talk about much, but mainly just flash some references and some examples. So quite a lot of people consider sparse universal graphs for forests. We just take graphs with no cycles, right? So these are forests, every connected component is a tree. We look at all forests with at most k vertices, and we want a graph without too many edges that contain all of them as subgraphs. There are lots of results about this, and we understand reasonably well the minimum possible number of edges in such a universal graph. Then another family that has been considered is the family of planar graphs and graphs with small separators. Now, some of the things I'll say will just be the buzzwords here, and it's not so important to really understand or know the notions. So if you know it, it's fine. If you don't, I'll not really use it, but this is just to give you examples of the families that have been considered. So there are quite a lot of work about universal graphs for the family of planar graphs, and some more general classes, which are graphs with small separators. Then simple to describe a family is just the family of all graphs with at most k edges. So we fix the number of edges, and then we can take these k edges and construct maybe a complete graph with about square root k vertices, or take a matching of size k edges. All the graphs of k edges, we want something that is relatively sparse and contains all of them. Here is another one. Graphs with maximum degree at most d. We look at all the graphs that have maximum degree at most d. So when d is 2, it will be just collection of cycles and paths. When d is 3 or more, it's more complicated. And again, there are quite a lot of papers that try to understand how sparse, what is the minimum possible number of edges in a graph that contains all of those as subgraphs. So two of the words that we had in the title was structure and randomness, and I'll try to tell you what I mean by these. So some of the results are proved by considering random graphs. We try to find a sparse graph that contains all subgraphs from some given family, and then we take some model of random graph. Usually the most common model is a so-called Erdős-Renyi binomial random graphs. And the reason it's called the Erdős-Renyi model is because the model was introduced by Gilbert. And actually around the same time, it's true that it was a very similar model was considered by Erdős and Renyi. And they indeed proved a lot of things about the properties of these random graphs. So So this is a correct name to call it the Erdős-Renyi random graphs. And often when maybe when we don't understand the structure of some problem well enough, then the simplest thing to try to do is just to take random graphs and try to see how good they are for the problems we are considering. And here is one specific example. So I told you that one family of graphs that has been considered is just a family of all graphs with k edges. So we want to ask, what is the minimum possible number of edges in a graph that contains every graph on k edges as a subgraph? And it turns out, so this was something that we did with Vera Sodi quite some time ago, improving some estimates of Babai, Chang, Erdős, Graham, and Spencer. And it turns out it's a correct minimum possible number of edges in a graph that contains every graph on k vertices with k edges as a subgraph is up to a constant k square over log k square. So in many of the things, the precise constant is not known, but it means that here both the lower bound and the upper bound are some constant k square over log k square. And the lower bound is just by some simple counting argument. So just there are many graphs with k edges, and we have to contain all of them. So by doing some simple counting argument, we show that our universal structure has to contain many edges. And the construction is probabilistic, so it's some version of the Erdős-Renyi random graph, only we don't take the usual random graph where we have labeled vertices and each pair forms an edge randomly and independently with the same probability. Here we really take some log k blocks of vertices with appropriate sizes, and then the probability with which we put edges between vertices in different blocks depend on the numbers of these blocks. And if we choose all the parameters correctly and we do the computation correctly, it can be shown that we can get a graph with k square over log square k edges that contains every graph on k edges as a subgraph. So this is one example where randomness is useful. And let me say something about structure. So some of the results for these questions are actually done by explicit constructions. And again, here I wrote one example. I'll not talk much about it. And this was with Mike Capalbo also quite some time ago. And it turns out that there is some explicit construction of a graph that contains all the graphs on k vertices with maximum degree d as subgraphs. This graph will have a little bit more than k vertices, and the number of edges, which again is optimal up to a constant factor, is k to the 2 minus 2 over d. So for example, if d is 3, then we need about k to the 4/3 edges. And I'm not going to say much about the construction here, but it's some sort of a product, or an appropriately defined product of a high girth expanders. So expanders are pseudo-random graphs which are sparse, but behave in many ways like random graphs. And they are of high girth. This means that they don't have short cycles. And there are known constructions of such graphs. And if we take appropriate graphs of this form and we define some product of them appropriately, then it can be shown that, that this has the right number of edges, and it contains every graph on k vertices with maximum degree d as a subgraph. Again, the lower bound here is by counting and is relatively simple. It again follows from the fact that we have many graphs on k vertices with maximum degree d, and because we need to contain all of them, then we need to have many edges. So this is about universal graphs. and this is what I meant by structure and randomness. But actually, I'll talk more about induced universal graphs. So this is a similar notion. Let me tell you what I mean by this. So this was first considered by Rado in the 60s. And we call now a graph G induced universal as opposed to universal, what was before universal. So it will be called induced universal, again, for a family of F of graphs, if every member of F is now an induced subgraph of the graph. Okay, so for example, here you see a graph, and you see that I took here these 4 red vertices, and I took all the edges that they span. And we will see that there is some algorithmic motivation to consider the corresponding question here. And the corresponding question to the one we discussed before, or that I mentioned before, is again, what is the smallest possible size of an induced universal graph for an interesting family F of graphs, an interesting finite family. And here we measure the size by the number of vertices. We don't care how many edges. We want to have a graph that is not too big, does not have too many vertices, and still every member of the family is an induced subgraph of it. Okay. And let me tell you some reason for trying to consider this problem, or for a possible algorithmic application of it. This is something that is called adjacency labeling schemes. Okay. So what is an L adjacency labeling scheme? So for some family F of given graphs. So this is basically, you can think about it as 2 algorithms or 2 functions. Label will be the first of them. So what it gets as input, it gets a graph H from the family, okay? And then it just assigns a label of L bits for every vertex of it. Maybe if the family was a family of planar graphs, you give me a planar graph with k vertices, and then I, or the function label, assigns to each vertex of it a label of L bits, of hopefully not too many bits. And then edge, that's another function or another algorithm, that what it gets 2 labels, and then it looks at the 2 labels, and depending on them, it tells us if the 2 vertices are adjacent or not. And it's important here that this function or algorithm edge, it only sees the labels. It doesn't know what's the graph edge from which it came, and it doesn't know the identity or the number of the vertices. It just knows the 2 labels. So if they are adjacent or not should be just a function of the labels. And you see that this is something that can be useful, right? So if I have an adjacency labeling scheme with a small number of bits, let's say for the family of all planar graphs with most k vertices, then this is an efficient way to store a planar graph in my computer. You will give me a planar graph. I'll apply this function label. It will tell me which label each vertex gets. And it will be just a few bits to each vertex. And I'll remember just these bits. I don't have to remember anything else. And now if you ask me if vertex number 17 is connected or not to vertex number 23, I just look at the 2 labels of them, and I apply the second function or the second algorithm edge, and it tells me if they are adjacent or not. So we can store it efficiently, and we can still access it. So this was actually a theorem. It's a simple theorem, but it's very useful and therefore important. So this is by Cannon, Naor, and Rudish. And what they observed is that a family F has an L-bit adjacency labeling scheme in the sense that I said, if and only if there is an induced universal graph for the family F with at most 2 to the L vertices. And the proof of this is easy, but let me just say it. So it's basically the 2 things are the same. You see, if I have an L-bit labeling scheme, then I can define, for the family F, then I can define a universal graph, namely every possible label will correspond to a vertex. So we'll have 2 to the L vertices, all the possibilities of the labels. And then the function edge will tell us which pairs of labels are connected and which not. And then you can see that this will be a universal graph, right? Because if we have a graph on the family, there is a way to assign labels to it. So these labels really tell you which vertices you have to take in this universal graph, and they will be connected or not connected exactly because the function edge is doing what it is supposed to do. And the converse is also true, right? If I have a universal graph, which is relatively small, has 2 to the L vertices, then the labeling scheme will just be, you give me a graph, because my big graph is universal, I find it as an induced subgraph of my universal graph, and the labels will be just the names of the vertices. So just the sequential number of the vertices of this big universal graph. And therefore, this is basically the same, and this is one motivation to consider it. And again, let me say something about what has been considered before, or some of the families that have been considered before. So maybe the most basic case, and about this I'll talk a little bit more later, these are general graphs. So we just take all the undirected graphs on k vertices, and we just want a universal graph, so a small graph that contains all of them as induced subgraphs. Okay, so this is general graphs. Then bipartite graphs have also been considered, bounded degree planar graphs, forest graphs of arboricity k. Again, I'm saying it's not so essential to know what every notion means, so this just to show that we have many families. Graphs of tree width k, and graphs of maximum degree d, so for odd d and for even d, this has been considered separately, and graphs excluding a fixed minor, and bounded degree outer planar graphs, and actually some more. And in each of these cases, we have some estimates. So we have some upper bound and lower bound for the smallest possible size of an induced universal graph, namely of a graph that contains each member of this family as an induced subgraph. Now, in some of these cases, the gap between the upper and lower bound is only a constant factor. So the two differ only maybe by a factor of 20 or something like this. And here I wrote actually all the examples for which we know this minimum possible number of vertices in a graph that contains every member of the corresponding family as induced subgraph up to a constant factor. So it is known for general graphs and for bipartite graphs. And as I said, I'll talk about this a little bit more later. It's known for graphs of maximum degree d, for even d, and a little bit more difficult for odd d, but in both cases up to a constant factor, for bounded degree outer planar graphs, and for forests. Now, in all these cases, I think I wrote it here. So there is no non-trivial family among all of those for which the correct constant is known. So there is always a gap, some factor, between the upper and the lower bound. So maybe in some of these cases it's a small factor, maybe 2 or 3. In some cases it's big, it's 30. So we understand it asymptotically up to a constant factor, but we don't know the constant, even for things that look simple. So look at graphs of maximum degree 2. So graphs of maximum degree 2, these are just graphs that every connected component is either a cycle or a path. It's very simple to understand what is this family, and it's not difficult to show that there the minimum possible number of vertices of a graph that contains each member as a induced subgraph is linear in the number of vertices, is between maybe 1.5k and 2.2k. I'm not sure these are the correct numbers, but something like this is known. And even here, although it's linear and the construction is relatively simple, we still don't know what is the precise constant. So it looks, and I'll try to tell you today about some results where indeed it is possible to determine also the constant. So I want to talk a little bit more about indeed one example. So this will be one representative example, which maybe is the most basic case and also the case that has the longest history. And this is just a family of all undirected graphs. So we have all the graphs on k vertices, and we want the smallest possible size of a graph that contains each graph on k vertices as an induced subgraph. Okay, I want to understand this, and just so let me denote it here by f of k, little f of k. This will be the minimum number of vertices in an induced universal graph for the family of all k-vertex undirected graph. And just to practice the definition, I have here one example. So I want to claim that f of 3 is 5. If I want a graph with the minimum possible number of vertices that contains every graph on 3 vertices as an induced subgraph, then the minimum possible number of vertices is 5. Let's see why this is simple. So it's definitely at least 5 because I have to contain a triangle, so a complete graph on 3 vertices. I have to contain an independent set on 3 vertices, and the two of them can contain only one common vertex because one is complete and one is independent. So this is 3 plus 3 minus 1, which is 5. Okay, then why this is an upper bound? Because what you see here is an induced universal graph. Let me show you. So here it contains a triangle on 3 vertices. Here it contains a path of length 2, right? Here it contains a graph consisting only one edge and one isolated vertex. And here it contains 3 independent vertices. And these are all the graphs on 3 vertices. Now, by now, you probably notice that my PowerPoint skills are very limited. So this actually is going to be the most sophisticated animation you're going to see here. Let me show it again. Right, so, okay, so this is okay. So we understand that this f of 3 is 5, and we want to understand what happens in general. So again, we want the minimum possible number of vertices in a graph that contains every graph on k vertices as an induced subgraph. So Moon showed in 65 that this number is at least 2 to the k minus 1 over 2, and at most some constant k times 2 to the k over 2. He had some specific constant, a different constant for even k and different constant for odd k by some explicit construction. And so there is still a gap of about k. Then there was some paper of Wiesing in the late 60s where he tried to collect what he viewed was interesting problems in graph theory, interesting open problems. And one problem that he mentions is to get better bounds for this f of k. Here is the result of Bolobash and Thomason from the 80s. They don't quite improve f of k, but still it's interesting. So they consider the random graph. And by the random graph, we take n labeled vertices. Every pair, randomly and independently, is an edge with probability 1/2. Okay? And then they could show that if the number of vertices is k squared times 2 to the k over 2, so a little bit more than what we have here, but not much more, then with high probability, this will be universal for the family of all k-vertex graphs. With high probability, it will contain all k-vertex graphs as induced subgraphs. And it's interesting, so this was in 81. It's kind of before people started to use in probabilistic combinatorics more sophisticated high deviation inequalities. And it's interesting that they could get this result just by using second moment arguments, so only Chebyshev inequality, basically. But then you have to do something clever because it's clear that second moment cannot yield good enough estimates to work against all graphs. So they do something. Now later people started using some more sophisticated high deviation inequalities and large deviation inequalities. And this estimate for the random graph was improved by Brightwell and Koyakawa in the early 90s. And they showed that for the random graph, some constant k times 2 to the k over 2 vertices suffice. So now it's comparable to the bound we have here. I'll tell you some more precise results about this later. And then there is this relatively recent nice paper that contains lots of clever ideas by Alstrup, Kaplan, Thorup, and Zwick. And they could determine the truth up to a constant factor. So again, we have the lower bound here. They got an upper bound of which maybe was by a factor of 20 or so bigger than the lower bound. So it's a graph with, I think, 16 times square root 2, something like this, times 2 to the k over 2 vertices that contains every k-vertex graph as an induced subgraph. Okay? And the new thing that I want to tell you about is really an asymptotic formula. So we can get also the correct constant, and there will be some negligible additive error term. So really the correct value of f of k up to a low order additive term is 2 to the k minus 1 over 2. So it's really the lower bound, and there will be an additive term that will be negligible. So, and somehow as a byproduct of the proof, we will also understand better what is happening for random graphs. So this is what I wrote here. So if we want to know the minimum n, so that the random graph gn1/2, we take n vertices and every pair forms an edge with probability half. We want the minimum n so that with high probability this graph will be k universal, will contain all k-vertex graph as induced subgraph. Then this is, again, up to a low order additive term, k over e times 2 to the k minus 1 over 2. And in fact, something stronger holds. If we look at the largest, so we look at the random graph, and we ask ourselves what is the largest value of k so that this graph is k universal, then this is always, with high probability, either the value of the maximum clique. You see, it has to contain, among all the graphs on k vertices, it has to contain a clique, complete graph on k vertices. So of course the k that we have here cannot be bigger than the maximum clique. So what is written here is that for most values of n with high probability, it's exactly the value of the maximum clique. And for some exceptional values of n, with probability that is bounded away from 0 and 1, then it will be 1 less than the size of the maximum clique. And I should mention here that, and this is somewhat surprising if you haven't seen it before, that if you take the random graph on n vertices, so those are pretty old results by Matula and by Volobash and Erdesh, that say that we really know the value of the maximum clique in it, of the maximum complete subgraph in it, with very high probability. So you take a random graph with 2 to the 2 to the 2 to the 10 vertices, so it's big, and then there will be some one specific number that I can compute. It will be roughly twice the logarithm base 2 of the number of vertices, but there is a formula. And with very high probability, this will be exactly the size of the largest clique. And again, for some exceptional values of n, there will be 2 possibilities, but so we understand the size of the largest clique, and something similar will be for the maximum k, for which this random graph is k universal. And then they'll tell you even something a little bit stronger about this. But okay, so I want to say something about proof ideas because I think there is something nicer. So it combines some probabilistic arguments and some group theoretic tools that I'll mention briefly. So again, let me denote by this capital F of k will be the family of all k-vertex graphs. And remember that little f of k will be the minimum number of vertices of an induced universal graph for this family. Right? And what we want to show, so here is just a more explicit statement of the theorem. So this f of k, the lower bound is 2 to the k minus 1 over 2. This was really proved by Moon. And the upper bound is the same, times 1 plus an additive error term, which is the same thing, times log k to the 3/2 over square root k. And the important thing is that this is something that tends to 0 as k tends to infinity. Okay. And the question is how do we prove it? So let me first say something about the lower bound. The lower bound is again counting, so this was done by Moon. It's not difficult. And let's see. So we have this graph G, which contains every graph on k vertices as induced subgraph. Now let n be the number of vertices of G. So it has to contain every member of f of k as an induced subgraph. And there are exactly n choose k possibilities to choose k vertices out of n. Right? So even if every k vertices will give me a different graph, I still have to get all of them. So definitely I need that n choose k will be at least the size of f of k, at least the size of the family of graphs that I'm trying to get. And f of k, it's not difficult to see that it's at least 2 to the k choose 2 divided by k factorial, because you first can take k labeled vertices, and then each pair can either be an edge or a non-edge. There are 2 to the k choose 2 possibilities. And then depending on the number of automorphisms of the graph, if the graph has no automorphisms, then we really counted every such graph k factorial times, according to the number of ways to place it on the k vertices. In fact, most graphs do not have automorphisms at all. They are rigid. So really the number of graphs on k vertices is basically the numbers that you see here. So we need this inequality, and if we solve it, then we get that n is at least 2 to the k minus 1 over 2. Okay? And you see from this argument that equality can hold here. Let's say that we want really equality. So equality will hold here in this left-hand side inequality if every member of this f of k, every graph on k vertices, will be obtained exactly once. So we would have this big graph, and it would contain every graph on k vertices exactly once. Now this is probably hard to get. I mean, it seems that it's too good to be true, and indeed it can be shown that that this cannot happen. So in fact, one can prove the following. I'll not say how, it's not difficult, that if we have any graph with exponentially many vertices, and our universal graph has to be with exponentially with 2 to the, at least 2 to the k minus 1 over 2 vertices, so any such graph contains some subgraphs on k vertices very many times, exponentially many times. In fact, not only one subgraph, but many subgraphs, and it's written here in some complicated way. Well, no reason to read it, but just say, so we cannot really hope to get every graph once. Some of them we will get them many times, and if the number of vertices of G is going to be 2 to the k minus 1 over 2, roughly, this is what we are trying to prove, then in fact most members of F, well, they can appear more than once, but they cannot appear more than 2 to the little o of k times, right? So this is just by counting, because n choose k will not be much bigger than the total number of graphs. So some graphs must appear exponentially many times, but we want that almost all the graphs will appear a very small number of times, so much smaller than that. Okay. So how do we get this? And as I said, if we don't know, or when we don't understand the structure of some extremal problems well, then maybe the most natural thing to try is to try random graphs, and this is natural, so we can ask ourselves if random graphs can help. And The short answer is no and yes. So there are bad news and good news. Let me show you what's the bad news here. So random graph as it is not going to be good because, for example, it's not going to contain a clique of size k if the size of the random graph is only roughly 2 to the k minus 1 over 2, and we compute the expected number of complete graphs on k vertices, then this expected number is going to be very, very small. Because in fact, a random graph of this size will contain a clique only of size k minus 2 log k. So it will be too small. In fact, the same will hold for every graph that we want to get as subgraph that has lots of automorphisms. You see the trouble, why does a random graph not contain a clique of size k? Because the clique has lots of automorphisms, k factorial automorphisms, and that means that when you try to place it in some place in this random graph, there is only one way to place it. We have only one chance to put it on these k vertices, and because of this, there are just not enough possibilities, and the expectation will be low, and with high probability, we will not find it. And as I said, the same will hold for every graph that has many automorphisms. But the good news is that, and I wrote it here with a computation, so that if we try to get a k-vertex graph that, let's say, does not have non-trivial automorphisms at all, so it's just a rigid graph, it doesn't have any automorphism, any non-trivial automorphism, then the expected number of copies of it that we expect to find in a random graph, let's see the computation here. So there are n choose k ways to choose k vertices. Then there are k factorial possibilities to try to place this graph on these k vertices. And once I decided to place it, then the probabilities that all the edges and the non-edges are where we want to find them is exactly 2 to the minus k choose 2, right? 1/2 raised to the power of the number of edges. So this is basically the expected number of copies. And if n is a little bit bigger than 2 to the k minus 1 over 2, so it's 1 plus little o1 times this, then if you plug it here, this is 1 plus little o1 raised to the power k. And if the little o1 will be chosen appropriately, then this number is pretty big. So at least in terms of expectation, we hope, or there is a chance to find every asymmetric graph, every graph with no automorphisms, as a subgraph. Now note that it's not, the fact that the expectation is big does not necessarily mean that we will find it there, right? But at least there is a chance to find it there. And this will be the plane here, okay? So here is a possible plane. We will try to prove the existence of an induced universal graph G for this family of all k-vertex graphs by constructing a graph with two pieces. So there will be a big piece that you see here and a smaller piece that you see here. The big piece will be random, so it will be a random graph, and it will contain all the asymmetric k-vertex graphs. So graphs that do not have too many automorphisms, it will turn out that technically we have to define it a little bit differently, but the intuition is that these are the graphs that do not have many automorphisms. And then all the symmetric graphs, graphs that have lots of automorphisms, then hopefully we will be able to find some structured, smaller piece that will contain all of them. Okay, so let's try to indeed do this. So we first have to define what we mean by symmetric and asymmetric. And it turns out that because of some technical reasons, this is a good definition. So I want to call a k-vertex graph asymmetric if it contains no induced subgraph with many automorphisms. And many is k to the 4m, where m is 2 square root k log k. Okay, so I don't want to have any induced subgraph in my graph that has about k to the square root k up to some logarithms automorphisms. So in particular, the graph itself does not have many automorphisms, so it can have k to the square root k maybe, but not more. But also, I want that every subgraph of it will not have too many automorphisms. And if if a graph is not asymmetric, then it is called symmetric, right? So maybe this is a symmetric graph because you see it has many pairs here that we can flip, so we have many automorphisms. Okay, and with this definition, it turns out that one can prove the following. So with high probability, if we take the random graph Gn 1/2, n labeled vertices, every pair forms an edge with probability half, and n is a little bit bigger than 2 to the k-1/2, so we add this negligible additive error term, then it contains every k-vertex asymmetric graph as an induced subgraph with high probability. And I'll not say much about the proof. So we basically bound the probabilities that a fixed such asymmetric graph does not appear as an induced subgraph by using some version of a large deviation inequality that is called Talleyrand's inequality. We need to have some twist there, and it's important to apply it to the correct random variable, which is not exactly the number of copies of this graph in our induced graph. But once we do it, so this is basically not too complicated. There are a few pages of computation, but it can be done, and this takes care of all the asymmetric graphs. So then the question is, and this was a more difficult part for me, and maybe the more interesting one, is what happens about these symmetric graphs. So somehow my initial hope, and it seems reasonable to expect that maybe we can apply some tools from group theory, so some results that are known about large subgroups of the symmetric group. This will be the groups of automorphisms of those symmetric graphs, so there will be relatively large subgroups of this symmetric group Sk, and then maybe we will be able to use this and get enough information to be able to construct this small piece that will contain all the symmetric graphs. And here is one example of a result that I thought indicated that things like that could be useful. So this specific one is a result by Baba improving earlier estimates by Bochert and Prager and Sackel. And for those of you who are still not sleeping, you may wonder how he managed to improve in 81 something proved in 89. But actually, this is a classical result, so it's from 1889, and so it's possible to do it. And the statement is the following: that every primitive, so primitive means a transitive, and also that does not preserve any non-trivial partition of the ground set into blocks. But it's not so crucial, so let's say it's some property. So every primitive subgroup of Sk of the symmetric group, which is not doubly transitive, so it does not have the properties that every pair of elements is mapped to every other pair of elements, is small, is of size roughly the size that I want to care about, right? Exponential in square root k up to some logarithmic factors. Now, if we could have indeed forget about primitive, then you see double transitive, maybe I wrote it here. If the automorphism group of a graph is doubly transitive, then it's very simple. It's either a clique or an independent set, because every pair is moved to every other pair. So if you have an edge, then everything should be an edge. And if you have a non-edge, then everything should be a non-edge. So if we just have to take care of a clique and independent sets, and we'll just add them. I mean, these are very few vertices to add. So the hope was that maybe, so of course the trouble is that we cannot assume that this is primitive. Mostly the assumption that this is transitive, the group of automorphisms of a graph would usually not be transitive. It's not true that every vertex is mapped to every other vertex. But still, for a while, I was hoping that I'll be able maybe to characterize all the graphs that whose groups of automorphisms is small. And I looked, but somehow it turns out that there are many of those graphs. I wrote here some example of a big class of graphs that have many automorphisms. So you just start from any graph you want. I wrote here random graph, but any graph you want on a little smaller number of vertices. So not k, but maybe k minus h square root k square root log k. And then you take in this graph some of its vertices and you double them. You replace each of them by an independent set of size 2 that is connected to exactly the same neighbors that the original vertex was connected. So this way you get many graphs, and all of them have lots of automorphisms because every pair like this, you can switch them independently of every other. So if you have x pairs, you have 2 to the x automorphisms, and this is just one example. So there are many other similarly constructed examples of families showing that you really have lots of graphs with many automorphisms, and it seems hopeless to really characterize all of them. But luckily, still something can be done, and here I'll not say much, but it turns out that still we can use enough of the known structure about large subgroups of the symmetric group, so basically about something called the minimal degree. So we want to use the fact that any such subgroup contains an element which with support, which is so the number of elements that are not fixed is quite big, but still is quite far from being almost everything. And then you can use this together with this connection proved that I mentioned before, proved by Kanan, Naor, and Rudish about the connection between adjacency labeling scheme and universal graphs, just to deduce from the group theory enough information about the graphs that will suffice for us to prove this second part, that it's not. I don't know what happened here, but right here. Yes, that there is an explicit graph with maybe 2 to the k over 2 divided by k squared, so much smaller number of vertices that contains all the symmetric k-vertex graphs as induced subgraphs. So here there is some work to be done, and if I had more, maybe 15 more minutes, then I could have said enough to give you the impression that if I would have had 30 more minutes, then you would have been able to follow. But let me not do it, so just say that this can be done, and then the two theorems together give us this universal graph. So let me just finish with a few questions. So there are many open problems about universal graphs for some other families. This proof that I kind of sketched here, it does work for several other families, but not for many other interesting cases, and it will be interesting to understand them somehow more thoroughly. I'm trying to focus on this photo, right? So let me, but just, okay. So, but let me still mention maybe two specific problems. So the first one, still we have a reasonably good estimate for this minimum possible number of vertices of a graph containing every k-vertex graph as an induced subgraph. And if you do the computation correctly, this is basically Moon's estimate, but I just did the computation more accurately. This is a lower bound, this is an upper bound. There is still quite some gap, and it will be interesting to close it. In particular, it will be interesting to get something in the lower bound, which is more than just the counting argument. So this is what follows from the counting argument. Can we get something that is bigger? I don't know. The second one that I wanted to mention is kind of a class of problems, and I think it's interesting. So this is something that I want to call the vertex random graph process. So there is something that people call the random graph process, and this has been investigated quite intensively, and there are many results, and I want to suggest a kind of a similar model. Okay, so consider the following a model that you can call the vertex random graph process. So you start from you have an infinite sequence of graphs, G1, G2, G3, and so on. G1 is just a single vertex. And then Gi plus 1 is always obtained from Gi by adding one more vertex and connecting it randomly to what you had before. Every vertex that existed before, randomly and independently, let's say with probability half, you can do other probabilities also, becomes an edge. And then you can ask, so here is actually an example of a statement, something that one can prove, again, using this connection to group theory. So with high probability, you look at this sequence, G1, G2, G, and so on, and you look at the first time that you contain a clique and an independent set of size k. So this happens at some point. You fix k. At some point, your graph will contain a clique and independent set of size k, and one can show that with high probability, as soon as this happens, then it already contains all the k-vertex graphs as induced subgraphs. So really the difficult thing will be to contain the clique and the independent set, and actually combining this with something called the Stein-Chen method, it implies that if n and k are such, so consider again the random graph, the usual random graph, if n choose k times 2 to the k to the minus k choose 2 is lambda, this means that the expected number of cliques of size k is lambda, then the probability that Gn1/2 contains all k-vertex graphs is really, we know to determine it, it's 1 minus e to the minus lambda square up to little 1. So this is true for lambdas that tends to 0 or tends to infinity, or for fixed lambda. This is always true. And the reason is basically because the probability to contain a clique of size k is 1 minus e to the minus lambda. This is because of Stein-Chen. And the probability to contain an independent set of size k is 1 minus e to the minus lambda. And the two events are roughly independent. So we really need both of them to hold. But I think that this model, this vertex random graph process, is interesting in its own. And as I said, there is a similar model that has been investigated quite a lot. It will be nice to get these results of this type are called heating time results. That exactly when some event happens, exactly when we contain a clique and independent set, then we already contain all k-vertex graphs. And you can consider some different events and try to prove that in this process, as soon as something relatively simple happens, then exactly at that time, something more complicated happens as well. So with this, let me finish, and thank you for your attention.
Questions? So in all your random graph models, you have 1/2 probability for an edge. Can you comment on that?
Yes, so one could try to take different probabilities for an edge, but then you could, it's possible to show that then you would need exponentially an exponentially bigger number. So somehow if you really want to contain all the graphs, then the best is to take a half. If we would want a family that is universal, for example, for all graphs with a 1/3 k choose 2 edges, then it would be natural to take a random graph with edge probability 1/3. But for this, it's best to take 1/2.
Any other questions?
Yes, this may be perfectly clear, but is it possible to tell for if somebody gives you a graph if it's symmetric or asymmetric according to your definition, or how hard it is to do so?
Right. So you mean how efficient it is to to know if it's right. So even finding the number of automorphisms of a given graph is not known to be polynomial, but at least is not exponential. So it's something roughly like graph isomorphism, maybe. But here I'm talking also about subgraphs, right? And then so I guess I don't know anything intelligent to say about it, but maybe it's interesting, right? Yeah. So one thing that I was told once is that if you don't know to answer a question or you don't want to answer a question that you are being asked in lecture, then you should compliment the one who asked it and say that this is a very good question. But this is but this is really a good question. Yeah. Okay. Thanks.
I have a more vague question, philosophical. In some sense, is there any connection with information theory? In some sense, the information of this universal graph contains just a very rough philosophical.
So I would say that maybe kind of the connection to the adjacency labeling scheme says something about some connection to information, right? Because it means it tells us how much information I can get from the labels of the vertices. So this is this connection, but maybe a shorter answer would be to say that this is also a very good question. But it's okay. But maybe it's a partial answer. Okay. Thanks.
Any more interesting questions or not?
Okay.
Does this problem has any, this technique has any link with Ramsey numbers?
So the connection to Ramsey numbers.
Would it give some insight on how to tackle problems on Ramsey numbers?
So I mean, the lower bound for Ramsey numbers is proved by a similar estimate as the one that estimates the biggest click in a random graph. But here it looks that it's, so maybe it's not directly related. It is something about, I mean, there is some, maybe I should, since you're asking, there is something that is known, so Ramsey graphs are graphs on n vertices in which the biggest clique and biggest independent set are of size logarithmic in n. So random graphs have this property, and one thing that is known is that Ramsey graphs, in some sense, they are somewhat universal. So they must contain, as induced subgraphs, all the graphs on some small constant times log n number of vertices. So this will not be good enough for me because it will not correspond to 2 to the k, but maybe to 100 to the k. But it means that indeed there is some connection, but maybe not directly to this specific question. Mm-hmm.
Any other questions? Okay, thank you.
Okay, thank you. Mm-hmm.